Good afternoon, everyone. How are you? I am Dr. Shikhar Tyagi from Department of Mathematics and Statistics, the University of the West Indies, St. Augustine campus, Trinidad and Tobago. Today, I am going to discuss with you a new lifetime model that we modeled on the climate COVID-19 reliability data with the different method of estimations. This new distributions was developed by us only. Us means my PhD supervisor, Dr. Arvind Pandey, my colleagues, Dr. Ravindra Pratap Singh, Dr. Abhishek Tyagi, and me. Right. So this is the outline of the talk, today's talk. So before going to start the why we need a lifetime distribution, we need to discuss the limitation of the existing models. So in that one, the first point is that complex density and hazard forms that are very difficult to handle. So we have seen in the recent time, so many lifetime models have been developed, but the form of those models are very complex and it is very difficult to handle for the real data analysis. And the second point is a limit to the model specific failure rates. So they have the certain type of failure rate shapes they can take. So that is the limitation of those models and the non-existence of the moments. So in that one, if the moments are not existing, so we cannot find out so many properties of the models and we cannot discuss all those things. So this is the one limitation that we have. And third one is, fourth point is the high parameters count leads to the computational overhead. So we have seen in the recent time the models that was developed about 4 parameters, parameters, 6 or 7 parameters model we have seen in the recent time. And when it comes to the real data analysis, it will becomes very complicated. And sometimes inbuilt codes are not able to analysis that data. So it is very difficult at that time. Insufficient flexibility for multi-domain data. So what happens, whatever the models has been developed in the recent time, we have seen that those models can be applied on some certain domains data. We cannot apply those data set on the different type of domains. So for that one, we have our goal is to develop a flexible parsimonious one parameter lifetime distribution that is suitable for the climate, epidemiological, and reliability data, and that we can use in other domains also. So that's why we developed the new distribution named as Arvind distribution. So the key advantage of that model is this is the single parameter model only, and even though it's a single parameter, it's have the versatile PDF shapes, and as well as this distribution has the different type of hazarded shapes like increasing, decreasing, and U-shaped that we rarely found while we have the single parameter and analytically and computationally tractable this model, and this model outperforms more than 70 plus rival models on the real data set. So now we will discuss the CDF and the PDF of the Arvind distribution. The CDF of the Arvind distribution is 1 minus e raised to the power minus theta x squared divided by 1 plus theta x. This is the CDF that we develop. I would like to outline one thing here that this is not the mixture of any model and we have not used any established method to develop this distribution. So this is the completely original distribution that we developed here. So when we are going to find out the differentiate of our model with respect to the x of the CDF. So we got the PDF, respective PDF, that is theta into 1 plus theta 1 plus 2x plus 2 theta x square divided by 1 plus theta x whole square into e raised to the power minus theta x square. Here x is greater than 0 and theta is also greater than 0. That means it's a lifetime distribution, and we validate these properties for CDF and PDF. We found out that CDF is always lies between 0 to 1, and as x tends to 0, the CDF tends to 0, and when x tends to infinity, CDF f was tends to 1. So the CDF was fulfilling the conditions for a CDF, and for a PDF, fx theta was greater than equals to 0, and when we are going to integrate over the range of 0 to infinity, fx theta was equals to 1. So that was fulfilling the conditions for a PDF, right? So here we have the shape of our model. So we can see that in this one, we have the different type of shapes of our model. So wide range of the variety of the shape of the PDF under the different values of the parameter we can see. So we can find out that here our model is right skewed and unimodal profile. And one interesting thing you can find out here, that as theta increases, the PDF peaks near to the origin. So when we took the theta equals to 0.01, the peak was about 5 to 10 somewhere, and when we just take 0.1, the peak was near to the 2, right? Similarly, as we took the different shapes again and again, when we took the theta equals to 20, we found that the peak was near to 0 only of our model. So that is the our model, that is the different shapes of our model for the different values of theta. And here we can find out that limiting behavior of our distribution when limit x tends to 0. So PDF will be equals to the theta, and when limit x tends to infinity, the PDF will be equals to 0. So it says that the model is heavy-tailed. Now we just talk about the mode. We find out the first derivative of our distribution, our PDF with respect to x, and we put equals to 0. So we got the form like 2 theta cube x raised to the power 4 plus 4 theta square x raised to the power cube plus 2 theta plus theta square into x square plus theta minus 1 equals to 0. So we cannot find out the mode in the closed form, but we can solve it numerically. Similarly, we can find out our quantile function, that is not again in the closed form, but we can find out it by using some numerical methods. So here we have the moments mu r, the rth raw moment, that again we are finding in the form of the integral. So we cannot find out the our rth moment, mean and sigma square, not in the closed form, but they are existing. So we have the some key insight from the next table. Here we can find out that mean and variance decreases as theta is going to increase. So we have the mean here. So mean when theta was 0.1, mean was 2.40. When theta equals to 0.5, mean was 0.9. When theta was 1, the mean was 0.6, and so on up to when theta was 20. So mean was 0.075 somewhere. Similarly, variance, in the variance we can see that it is decreasing as the theta is going to increase. So this is the property that our distribution have. The skewness is always positive, so our model is positively skewed or right skewed only, and kurtosis is less than 3. Here we can see that our kurtosis is less than 3 for most of the parameter. So it says that our model is plateautic, and peakness increases with theta. Means if we can see here, as theta is going to increase, so kurtosis is also going to increase. So in that one, peakness will increase as the theta is going to increase in our model, right? So all major central tendency measure decrease as theta is going to increase. All right, and theta acts as a scale and gradient parameter, and positive skewness confirms that right skewed nature suitable for the lifetime data, and plateautic for small theta, and transition towards the leptokurtic as theta grows. So after that we have the mean deviation, that is also not in the closed form, but we can find out it numerically. All right. So here we can see that mean deviation about mean is always, sorry, mean deviation about median is always less than mean deviation about mean. that is shows that the consistent with statistical theory, mean deviation about mean is minimum. So here we have the mean deviation about median, that is smaller than the mean deviation about mean, right? You can find out that one. It is always less than mean deviation about mean, right? So now we just talk about the reliability and hazard rate functions. So the survival rate function is e raised to the power minus theta x square divided by 1 plus theta x, and hazard rate is theta equals to 1 plus 2x plus 2 theta x square divided by 1 plus theta x. So here we can see the different type of shapes of our hazard rate model. Okay, so here we can say it is strictly increasing when theta equals to 0.5, theta equals to 1, theta equals to 2. And as we are going to take the theta greater than or equals to 5, so we can see the changes in the shape. It started. So now at theta equals to 10, it is now decreasing failure rate. And for theta equals to 20, 30, and 50, you can see the U-shaped hazard rate function here. So as limit x tends to 0, the hazard rate will be equals to theta. It's a constant like the exponential distribution. But when x tends to infinity, the hazard rate also tends to infinity. It will increase, right? So after that, we just discussed about the stress strength reliability here. So you can see that if x1 follows the Arvind distribution with parameter theta1, that is strength, and x2 follows the Arvind distribution with parameter theta2, that is our stress, and both are independent. So at that time, the stress strength reliability, that probability x2 is less than equals to x1, will be equals to 1 minus theta 1 integral over the range of 0 to infinity 1 plus 2x plus 2 theta 1 x square e raised to the power minus theta 1 plus theta 2 x square divided by 1 plus theta 2 x into 1 plus theta 1 x whole square. So we solved this stress strength reliability in a numerical through the numerical method. So here we find out that as theta 1 is going to increase when we fix the theta 1, sorry, when we fix the theta 1 here, so we are finding that the stress strength reliability will increase as theta 2 is going to increase. Theta 2 is 0.5, so we have the stress reliability 0.5, theta 2 is 1, so it is 0.65. When theta 2 is 2, it is 0.77. So it is continuously increasing. Similarly here 0.34, 0.5, 0.64, 0.79, and so on. So again it is increasing for when theta 1 is fixed, but theta 2 is increasing. As well as when we are going to increase, we are going to fix theta 2. So stress strength reliability will decrease as theta 1 is going to increase. So here we can see that theta 2 we fix at 0.5. So now it is 0.5, then 0.34, 0.22, 0.11, and 0.06. So it is decreasing, right? So this is the 3D graph of our stress strength reliability. That is a very smooth one. A smooth surface confirm that well behaved stress strength reliability, and symmetric about theta 1 equals to theta 2. So here you can see that when theta 1 and theta 2 both are equal, so at that time we have the stress strength reliability is 0.5. So means it is symmetric at that time. Okay. Now we discuss some other properties of the models, that is the ith order statistics, the PDF of the ith order statistics we find out here, as well as mean residual time and mean past lifetime, and cumulative hazard rate and stochastic ordering we find out. And here we can see that mean residual lifetime and mean past life is not in the closed form, but we can solve it numerically again. All right. As well as we discussed about the inequality measures like Lorentz, Bonferroni, and Jenga curves. So here we have the table for all these curves. So here we find out that inequality increases with theta. All right. So theta is equals to 0.5. So at the time it was 0. So basically, when theta is going to increase, so at that time the inequality is going to decrease when we have the theta equals to 0.5. So at that time it was 0.01, then it will become 0.0067, and then it will become 0.0051. Right. So when theta is going to increase, we have the lower values of Lorentz and Bonferroni curves, but Jenga curve will going to increase because the Jenga curve value is 0.9079, then it will become 0.9393, and then when theta equals to 5, it becomes 0.9537. Right. So here we have used the 6 classical estimation method to estimate the parameters for our model. So we have used maximum likelihood estimate. This is the maximum likelihood equation that is not in the closed form. So we can use the some numerical methods like Newton-Raphson, and we have the use the maximum product spacing method. We have used the ordinary least square method, weighted least square method, Kramer von Mises method, and Anderson-Darling test. Anderson-Darling method for the estimation. Right. And for the asymptotic confidence interval, we observed the Fisher information matrix, and based on the Fisher information matrix, we find out our confidence interval, that is theta cap plus minus z alpha by 2 square root of variance of theta cap. All right, and under the regularity condition that theta cap minus theta divided by the variance of theta square root of the variance of theta cap tends to normal distribution with parameter 0 and 1. So before going to the data analysis, we just perform the simulation study, and we design our simulation study in the following manner that we have set up the 2500 replication for each scenario. We took the different sample size that n equals to 10, 20, 40, 60, 80, 100, and we took the different values of the parameter like 0.5, 1, 2, and 4, and we use the random variates via the quantile function inversion method, and all 6 estimated computed per replicates. So uh, we check our simulated results through the performance metrics. For point estimation, we use the expected value, mean square error, and average bias. For interval estimation, at the 95% asymptotic confidence interval, we use the average lower and upper lower limit of the interval, and average width and coverage probability that we discussed here. So these are our, this is the list, this is the table of point estimation here. Here we can see that for different values of the parameter, as n is going to increase, we can see that the MSC is decreasing with respect to the sample size is increasing, and absolute bias is also going to decrease for all the methods. But you can find out that with respect to all 6 methods, the MSC or biasness, absolute biasness of the, sorry, average biasness of the MPS method is lowest in compared to other 6 methods. So MPS is consistently achieved the lowest MSC across all theta and n. Right. So in the simulation study, we found that the MPS method, maximum product spacing method, was performing better than other methods in compared to MLE, ordinary least square, weighted least square, CVM, and AD. Right. Here, this is the simulation results for the confidence interval. Here we can find out the, we can see the lower and upper asymptotic limits, and this is the average width, and this is the coverage probability for all the methods. We can here we can find out that the coverage probability maintains the nominal 95% level even for the small sample, and average width decreases as n is going to increase and interval is going to tighten, and asymptotic confidence interval reliable across all the values of the theta here. So The overall conclusion that we got here, that is the absolute bias, average bias, and the MSC tends to zero as n tends to infinity for all estimators. That implies that for the consistent and asymptotic unbiasedness, MPS is the most preferable estimation method with the lowest MSC. CVM is the least favorable method here, and expects accepts MPS. All estimators slightly overestimate the theta, and asymptotic confidence interval sustain the 95% nominal coverage with it sync with the n is going to increase. So MPS is the best one for us, and CVM is the least favorite. Right. So real data. Here we just discuss the three data set. All right. From the climate, epidemiology, and reliability, three data set we use, and we compare our Arvind distribution with 17 plus distributions like Lindley, inverse modified Lindley, exponential, inverted exponential, inverse Rayleigh, inverse X gamma, inverse Weibull, inverted uh, NH method, inverted Tocleone, Bohr-Hatake exponential, Maxwell, Laplace, inverse Lomax, exponential Poisson, and Rayleigh. These are the distribution that we compared with our model, and for the goodness of fit and model selection criteria that we use, that is negative likelihood function, AIC, BIC, CAIC, KS, statistics, and p-value. So these are the box plot of our these three data sets, right? And this is the analysis of first data set. So we got the estimated value of the parameter theta is 0.19 with the standard error 0.03, and the negative log likelihood value is 39, and AIC is 81, and the p-value of the model is 0.96. That is quite better than any other model. So here we find out the Arvind distribution has the lowest negative likelihood value, AIC value, BIC, CIC, and KS value. So highest fit value we are getting, that is 0.96, that uh, shows that the excellent fit of the data set. Okay, model is fitting excellently to the data set and outperform even two parameter models here. Okay, like inverse Weibull and inverse gamma and other models. And this is the case plot and histogram plot of our empirical versus fitted CDF for data 1. So here we can see that model is fitting very well to the given data. For the second data for the COVID-19 daily cases in India, we got the, for the data analysis, we got the value of the estimated parameter is 0.0071, and with the standard error 0.0013, and the likelihood value, negative likelihood value is 95, with the p-value of the case statistics is 0.50. Here we find out that Arvind distribution provides the best fit among all competitors for COVID-19 data and lowest AIC. That is the difference between the lowest AIC of our model and the other model is about 3.5, that is quite high. So it shows that the model is utility for the epidemiology data in the modeling, and this is the plot of empirical versus fitted plot of the for the case test. So it is showing that model is fitting very well for the given data. Now comes to the time to failure rate. So reliability data, here again we find out that the negative likelihood value of our model is 0.40, uh, 40.95, and AIC is 83.91, and the p-value of the case test is 0.77. So Arvind distribution again achieved the best fit overall with the lowest negative log likelihood value, and AIC, BIC, CIC, and KS value, and highest p-value. So it confirms the versatility for the reliability and engineering data. All right. So again, this is the plot of empirical versus fitted CDF plot for the third data set, and is showing that model is fitting very well. So here and after that we use the different method of estimation for the real data also, and here we found out that weighted least square method is performing better than any other mode, fitting very well in compared to any other model. All right, the in the for the given data set, and for the third data set we have ordinary least square that is fitting much better in compared to the any other method, right? Uh, for MLE, the p value was 0.77, but for the ordinary least square, we got the value 0.99. And for first data set, we were getting the p value for MLE of the cache test was 0.96, but for weighted least square, we were getting 0.98. So we got one interesting observation here. So in the real data set, ordinary least square, weighted least square, and CVM achieve higher p-value than MPS. That is completely a reverse trend compared to the simulation. As we have seen, this highlights the importance of using the multiple estimation method in the practice. All right. So the summary of the contribution here, we drive the new distribution that named Arvind distribution with single parameter flexible, that is very flexible, and we are getting the versatile shape of the PDF as well as for the hazard rate function, and the mode quantile function moments skewness and kurtosis are existing. Maybe they are not in the closed form, but they are existing, and mean deviation and other properties are already there, and we just find out the stochastic ordering that is very useful for the reliability theory. And for the estimation, we use the six estimation method here. All right, and MPS was best overall for the simulation study, and CVM was for least preferred. And asymptotic confidence interval and with reliable coverage, we find out. And superior real data fit, basically, it is our distribution is very well fitted to the and providing better results for climate data, COVID-19 data, and reliability data. And it is performing better than more than 17 models, 17 existing model. So here, the key takeaway and future direction for us. So a single parameter model can outperform multi-parameter alternative when the distributional form is well designed. Second is the Arvind distribution is viable universal alternative for the lifetime data across the diverse domain, and the MPS estimator offers the best balance of bias and efficiency for this distribution. And the future research direction that we can do here, that extension of the sensor data type 1, type 2, and progressive censoring, stress strength model under the various classical and Bayesian framework we can do, and regression modeling we can do by using the Arvind distribution as a baseline distribution, and we can do the extension to the bivariate and multivariate distribution of Arvind distribution, and Bayesian inference with informative and non-informative prior that we can do. Thank you so much, and these are some references that we used in our paper. Thank you so much. If you have any query, you can ask in the comments, right? Like, subscribe,